So here's our question. Is y equals x cubed an implicit solution to the differential equation xy prime equals 3y going through the initial condition of the origin, y not equals 0? Right away with no math, no, it's not. Why? Well, because it's asking for, is it an implicit solution? And no, the equation is explicit. So if it's a solution or not, it's an explicit version of it because it's y equals. So I'm going to read, right now the answer is no. I'm going to change the question so we can do some math, otherwise it's a mad short video. And I'm going to put explicit. So is it an explicit solution to the differential equation? All right, y equals x cubed, it's explicit, it's an explicit function. So at least we've satisfied that part. So now for it to be a solution to the differential equation, it has to do two things. It has to go through the initial condition, satisfy the initial condition, and it has to satisfy the differential equation. So let's check the initial condition first because that's the easiest. It's supposed to go through the origin. When I make x equal to 0 and y equal to 0, does that solve the equation? Is the point 0, 0 on the curve y equals x cubed? Yeah. So we've got that done. The origin is on the curve. So we've satisfied the initial condition. The next thing we have to do is show that it satisfies the differential equation. So this differential equation, but I'm going to replace this equals sign with, I don't want to make this equals yet. I want to have this piece equal to the left side, and the right side equal to the other. So I'm not setting them equal yet. I want to show that they're equal when y is equal to x cubed. So now let's look at the left side here. The left side equals xy prime. If y is equal to x cubed, then y prime is equal to 3x squared. So that would be the left side. The right side is supposed to equal to 3 times y. Well, if y is equal to x cubed, there's the left side and right side, both written in terms of y, and that makes the left side equal to 3x cubed and the right side equal to 3x cubed. Now I can say it's equal. So I can say left side equals right side, therefore this y equals x cubed is a solution. So it satisfies, it's explicit, and it satisfies those two properties. Goes through the initial condition and satisfies the differential equation. So now we've answered that question. Let's do a little bit more with this question. So what I'm going to do is, I was given this solution, but I'm going to go back to the differential equation here, and I'm going to pretend that I didn't have the solution. So I'm starting with the differential equation, and because the equation is separable, I've decided to write this as dy dx instead of y prime. So I can multiply the dx up. You see from this step to this step, I put all the x's on the x side and all the y's on the y side. Then I can integrate both sides. So the integral of 1 over y with respect to y ln absolute value of y, 3 ln absolute value of x plus, we need a constant on one side. How do we get the constant? Initial conditions. But let's just wait for a second here. I already kind of have a problem with this question. If I was to try and get the c right now, I would be making x equal to 0 and y equal to 0. So I'm taking the ln of 0, and that's negative infinity. We can't do that. Where did that problem occur? Well, it's also a problem up here because when x is equal to 0, this whole 3 over x side dx is undefined. The original problem, actually, the original question had a problem because if I write it as y prime equals 3y over x, x can't be equal to 0, or x equals to 0 is a place where that formula, the 3y over x, is undefined. So that's an issue. That's going to be where the point when x is equal to 0, any place where x is equal to 0, we've not satisfied the conditions of the existence and uniqueness theorem. So we're not promised an answer, and we're not promised a unique answer. All right, that said, let's proceed. We got down to this step. Let's just proceed ahead, knowing that there's probably an issue. So I'm going to raise each left side and right side to the exponential. So e to the ln absolute value of x of y, and e to the ln this side. So to get rid of the lns, I put e to the left side, e to the right side. This 3 I'm going to bring in as an exponent. And then I can think of this whole side as e to the ln x cubed, which is just x cubed, times e to the c. Common basis, add the exponents. And that's where I've got an e to the ln y. That's where I've got this stage here. Now, I've dropped the absolute value bars. Because any sort of plus minus issue I can deal with this constant. E to the c is a constant. I'm going to replace it with k. If I don't, if I figure out what c is, then e to the c is just that constant. Now, how do I get this constant? Well, initial conditions. If I make x equal to 0 and y equal to 0, here's where I see the problem. K could be anything. K could be 1, and that would be a solution. That was our original answer. But I guess K could be 8, and that's still a solution as far as it goes through the origin and it satisfies the differential equation. You can repeat what we did earlier in the video and verify that y equals 8x cubed is also a solution, an explicit solution to that differential equation. So we've got multiple, I guess I've got infinite solutions. I can make that k equal to any number. So I've got infinite solutions to this differential equation. That's because we violated the assumptions of the existence and uniqueness theorem at the point where x is equal to 0. If I would have said any other initial condition, like x equals, so here's our differential equation, and I'm going to make I'm making it go through the origin. If I would have picked any other x value, so say I would have made it go through the point 3, 0 instead of the point 0, 0, then when I got to this stage to find k, I would make x equal to 3 and y equal to 0, and I would have got a unique value for k. I guess I would have got k equal to 0 would be the case. So the curve would have been y equals 0. That satisfies the initial condition, goes through the point 3, 0, and satisfies the differential equation. If I would have picked an initial condition, a different one, like 3, 7, then, well, let's make my life easier, 327, just to pick numbers. Then y would be 27, x would be 3, so I'd get 27 equals k times 27, so k equals 1. I would have got a unique solution. That's because at the point 327, I'm not dividing by 0 here. The y prime is defined. So there was two things that we were looking at in this video. The starter thing, the most important thing, is how to verify that something is an explicit or an implicit solution to a differential equation. The second thing we talked about is we hinted at consequences of not satisfying the assumptions of the existence and uniqueness theorem.